So we have done so far only half of the job. We have seen the Galois group acting on the automorphism group. So this part we understood is which is automorphisms of behavior to itself that behavior with field, and we have defined what is field from a given tensor on the base field K. We have extended to a tensor on the top field L in a natural way. So I think I said it in the very first video, but let me recall it again. So this is our main theorem. So this is our main theorem. So we'll try to prove it this time. So the main theorem says that all the symbols are as before, so I'm not mentioning them. So it says that it has a one-to-one correspondence between these two sets. So the notations as before. G is the Galois group, and we have seen G acting on H. G acting on the automorphism group. So the H1 makes sense, which is the one co-cycle more the one co-bound. And yeah, on the left hand side is all such twisted L over K form of V5. And this is a bijection. In fact, it's a base point preserving bijection. It's a base point preserving bijection. And so, what are the base points? The base points are pretty obvious because in the left side we have the isomorphism class of V5 itself. And in the right side there is this cocycle which takes every element in the Galois group to the identity in the automorphism. And it will be pretty clear from the way we will define at least one map from one side to the other that the base point here, base point in the left side will go to the base point in the right side. So that should be clear from the way we will define these maps. But, in order to define those maps, we have to check a lot of things. So let's start with one part, which is still the shorter part compared to the other one. So we have to do two things. We have to give a map from the twisted forms to the H1 and vice versa. So let's start with the first one. So this is giving uh, going from twisted form to a element in the H1, so to a cohomology class. So what we need to do? So we have a twisted form in hand. So let's start with this isomorphism plus of this because remember we are taking the isomorphism plus of twisted forms. We are not taking all of them. If they are isomorphic over Q, we will get them as same thing. So this will claim the twisted form of L. So by definition, what we know that WK psi Q. There is a L, in fact, there is a L isomorphism between these two L objects. L So what we do, we choose one such isomorphism. So let G from, let's say from the other side, we make the notations here, B and L isomorphism. And then we will define, so we need to define a map from G to odd phi L, uh, which is a cocycle basically. So with this G, we define this map from G to odd phi L, we're taking in sigma. So what we'll do is, so this E, so we should go to our sigma. So how is it different? So we're starting with phi L. So we can talk about 1 tensor sigma, or maybe 1 tensor. Okay, we can talk about, or maybe let's write it in short. Because we have already seen G acting on Earth. So let me refer this action like this. So this will still be, so this will be an element. Uh, so this will actually be a map in W. But to go back to here, just compose it with changes. Okay. This is the map. And we need to check a few things. Firstly, we need to check it's a cosine. So, it's a cosine. So 1 cosine. That's obvious because we have sigma pi. What we need to check. This should be G inverse sigma pi acting on this, and this can write it as uh, so sigma G inverse, and sigma of power G. This we can write, and we can write this, and we can take the sigma. What? This is by definition A of sigma. This is sigma A of tau. Right? So it's a one question. Right. So indeed this shows that the class of P is indeed an element of this. Right? It's clear, but that's not all because we have started. We have assumed that these two are L isomorphic, but we have chosen one particular isomorphism. So we need to really check that this doesn't depend on the chosen isomorphism, and that can be done because uh, so this independence of choice of isomorphism. So what if there is another isomorphism? If A is another isomorphism, then basically we need to show that these two associated co-cycles are same in the whole H1. I mean they're co-homologous, right? We say them co-homologous. Just set this to be just, and then as we know this we'll just do so C inverse means G inverse H, B of sigma, which is just uh, what is it? It's just H inverse. So this B is basically the cocycle associated to H. Okay, when you're writing this, and then sigma of C just this because C is H inverse this, and so all of them will cancel out and this right. This is just yeah. So this is again by definition they are co-homologous. So these are two cocycles are co-homologous. So one cocycle is co-homologous. So one such C exists as well. This precisely this relation holds. This is so this is well defined, and we have gone from one side. Uh, we've gone from this side to the other side. Okay, so this is easy. And now, as I said, so this will be mapped in one direction. And now let's just check the base point result. So the base point in the left side is just the class of V5, and it's isomorphic to itself, of course, via the identity map. So identity map is one such isomorph. And we have seen that any such isomorphism uh, will do the same thing. You can pick identity in particular, and that will correspond to whatever the element. That will be just what will be the element. So G is identity. So G inverse sigma G. Again, that's the identity network. Because G is identity. So sigma takes identity to identity, and you compose it with its inverse if you get an identity. So the base conserving thing is just two. But again, we need to be a map in the opposite direction. And we have to again show that those two maps are indeed inverses of each other, which is still a long way to go. Now, let me for now just define the map in the opposite direction. Maybe I will try to show that they are inverses of each other in the next term. So let me just give the map in the other direction, and it's tricky. It's not as straightforward as this is. So this is just going from cohomology class to a two-step. So we start with an element simply on the right hand side and start alpha in this. Then alpha will be some class of a cocycle A. And now what we will do, so we have this A, and now I am to define an action. So remember there is already one action of G on VL, right? It's just you take an element in the Galois group and just act it on the second component of VL, because every element of VL looks like a finite sum of simpletons. So you can just act on the second component, which are just coming from L. You can act the sigma, because sigma is really an automorphism of A, a field automorphism. So that's the usual action. But we will define another action on of G on VL. So define uh, what is called the twisted action. So what we will do, we take twisted action G on VL. We take a sigma. We take any element of VL. We do this. So by this means the usual action that I just said on the second point, the sigma bracket. But we don't just stop here. We multiply with A of sigma. So A of sigma is also an element of uh, what it was. Right. A was just a map from this to this. It's the cocycle condition. So A of sigma will be an element in the. Yeah. So A of sigma is an automorphism of VL, and sigma of X is an element of it. So that is just A sigma of sigma. So this is the twisted action. But you need to verify it's an action. That I leave it to it's easy. Verify that it's an action. Verify that it's an action. And remember here you need to really use the similarity of the action, because right, so or not the exact similarity, you just have to uh, use this property that, so if you have an element in the value of sigma, if you have an say automorphism, I mean an element in auth phi A, which is phi, and if you have an element in V, okay, so you have all this. So phi f dot x is really an element in V, okay, because f is an element. Let me write it here. So sigma is in the value group, x is in VL, and f is in Yeah, if is an if dot x means just f of x. See, this is just f of x. So this will be an element in real, and sigma also acts on real, but just trivial action. I mean, trivial means the usual action. It's not trivial, so it's usual. So this you can very easily check that. This is just sigma acting on f. And remember, G also acts on the automorphism we are just saying by conjugation. I think I think I mentioned it last time. This is actually, at least this both sides make sense because right side is eventually, sorry, the left side is eventually an element in, so f of x is an element in real and sigma dot t. So this is an element in real. And the right side, sigma dot f and sigma dot x. So sigma dot x is an element in V, and sigma dot f is actually automorphism of V. So, and the dot in between is just the, this is an automorphism and this is an element. So just this of this. So this means this, which is a map, and you evaluate it as this value. So this will again be an element in V. And just check that they are safe. So both the sides actually make sense. They are in the same thing. V. Just check with this. And from now we'll equate VL with this action, which is defined by star. And we'll denote this VL equal to this action as VL with A in the beginning. And just let W to be, so this is a G set, right? Because G is acting on this. So it makes sense to talk about the invariance. These are just so these are all elements in real, so that A of sigma, sigma of x, for any sigma, the Galois. Okay. And so now we just have to make sure that, uh, so, or maybe we can do one thing from now. So W is defined in this way. And so now we can talk about W L, which is nothing but A V L 3L. And so from this to this, we have this method. So any element looks like x, which is in the fixed set in the W, and an element in A, which is like this, and we just send it to L. So this is a L isomer. This, I think it's, I did it in the first time for vector space. I think it's same proof will work like this. So what we did is, next thing what we need is, I mean, we need to make W, and we need a tensor on key to make it, so if the tensor is say psi, so that will make W comma psi a twisted form because WL is already isomorphic to phi, that is done. So we need something like this. So uh, next we make it scale, and for that we need to define a tensor on W. I mean, tensor of type PQ. So this PQ is fixed from the very first. Right. And this we can do because, so let me just give a brief idea of this thing because writing everything will take time. So let me just do an overview. So what we do is, uh, so remember we have So we need to define a tensor like this. Okay, cool. So if we can do this, so we look at this. So this three, L, like this. Look at this. Okay. So what is this? So remember this. So if is say this now. Okay. So this will just what it will be. So this is an isomorphism. We can talk about. Let me write it. This will make more sense. So from WL tensor Q term to WL tensor P terms. So first we will define a tensor in the top. That is on L. So we need to define such a map. So what we will do, we first go to VL this via just F tensor on each component Q times, and similarly here on each component P times. And then this already we have a map phi L. There is a tensor of type PQ on WL. So we are defining it to be this combination. We will call it fuel tilde. So fuel tilde is defined as first you go like this here, and then this define was this. And then we need to show fuel tilde descends if we tensor of type PQ and W. So far we have got a tensor of type PQ on WL, and we need to show that it comes from some tensor below, i.e. there exists phi uh, map from this to this, so that sorry, there is a phi. Phi. L is just this one. Fuel tilde, which is defined like this. And so if we can show this, then we'll be mostly done. I mean, done in the sense of just defining them. Still not, we have not shown that they are inverses. We will show it next time, otherwise we will. And now, in order to show that it really descends to some map, it's not an easy calculation, let me tell you. But at least, uh, right. So the thing is, we need this following lemma, which I think is kind of similar to what I did at the end of the last video. So at the end of the last video, we showed that when uh, mm, a linear map descends from a k-linear map. So we did this. Right. So we did this. So here we show that if it's in the fixed set, then we do. This exactly same proposition holds here. That means when a tensor on top comes from a tensor below, because that is what we need. We have a tensor on top. We need a tensor below, so that comes from that tensor. And the statement is as follows. So let me just write this statement. The proof will be exactly similar. So following are equivalent. All the notations are as before. There exists a tensor phi of PQ type on. Okay, so let me do it for generic. So don't go with the. So, so it should be understood that this V has nothing to do with that. Just a separate thing. Which that phi L is shy. it should be understood from the context of what is he and she. I mean, it's still for the sake of completeness. Just mention. So P keyword fixed as before. G is the Galois group as always. And so shy is tensor of type PQ on WL. We need some what is we need some phi such that phi is there is same as showing that uh, phi of psi is psi for what am I saying? Sigma of psi is psi for sigma in the Galois group. See, these things are pretty confusing. As the, at least the notations are pretty confusing because there are so many actions are going on the same. And this can be shown pretty easily. And we'll just assume this result because otherwise it's a very long calculation. I can refer you the source where you can find. Otherwise, it's just too boring because it's just a 2 or 3 pages long calculation that this phi tilde. So what we need from this lemma phi, we need that this phi tilde is fixed under the action of G, right? So then it will come from some phi below, and that I will mention the source where you can find one. So I will just attach that link with the video. And so yeah, so if you assume just that, then you've got at least a element, I mean a k object W phi. Phi is what that phi that will come from this limb if you assume that big result. I mean not big, I mean this lengthy result. So we have got a k object, and that's a twisted form because W will is significant V, and also phi L is just phi tilde L. So yeah, and so if you assume that, we have gotten a L object. I'm sorry, we have gotten a key object W, comma phi. And now we just uh, yeah, so we just have to show that these two things, the composition of these two maps that we have defined in this term is identity on the respective domain. Right. And besides that, I need to check a few more things that I will mention next time because these are just obvious things to check. Right? Because we started with one, so we started with the alpha, and we pick alpha is class of some cosine. What if there is another cosine? That we needed to do. Right? Because what if alpha comes from a cosine A, but at the same time it comes from a cosine B? That means A and B are cohomologous, but then the resulting action will be different. Right? The twisted action, twisted by the cocycle A and twisted by the cocycle B, both will be different. So you have to show that those two things are really isomorphic in the left side, in the twisted forms. So that is one thing I need to do. And second thing, we have to show that it's a twisted L over K form. We have shown that WL is isomorphic to V. That part is okay. Uh, And I think the other part is also okay. I mean, the shy L, whatever the shy will be, W comma shy, it's the twisted form. And to check the shy L is actually phi L, right? That is what we need. But I think that's obvious because by construction, shy L is, by this lemma will be phi L tilde. And phi L tilde is defined to be like this. So I think that will follow, but again I will check it. But yeah, we have to check that other thing that if alpha comes from another cocycle, how are they related? That is an isomorphism and all. And then we will be in a position to directly prove this thing. And after that, we will try to give few examples of these things, where this is useful, why we are doing these things. I think I have already mentioned one example. Let me show. Maybe not. Yeah, so I mentioned already one example, the central simple algebra that is split by L. So, yeah. So I will try to give some specific example of tensors of type sums 0, 0. 0, 0 tensor is just a vector space equipped with method. Just a basic vector space. Tensor product equipped with a type 0, 1 is just a vector space with an endomorphism. I mean a k-linear map from V to K. right? Tensor product, tensor of type 1 is just in V equipped with a special endomorphism from V2. So I will try to give examples in a few situations. And let's see. So next time I will do the rest of the things. Or maybe I will need another video because these things are easy to state but difficult to prove with all the actions and all the symbols. So let me start.